What I want to talk about is a topic that has been with me for, I think, almost 10 years, which is to worry about regularization. What type of regularization, what type of prior information can we use to solve inverse problems? And in this talk, I will mainly focus on an idea that we developed now already almost 1.5 years ago, which was to use as a data-driven regularizer a neural network and see in which contexts and in which framework we can couple this with inverse problem solutions to still have something where we can prove things about, where we actually have some solution guarantees. Okay? So this is roughly the idea of this talk. And I mainly have this slide here, not to forget what I want to convey myself, just to be reminded. So the main messages of the talk are that I think recent ideas in machine learning, and in particular deep learning, have very interesting and offer very interesting opportunities to all kinds of different applications, but in particular to inverse problems for two reasons. First of all, there are a couple of recent works which show that complementing inverse problems models, inverse problem solutions that we classically used with more data-driven components given by neural networks can give you very high quality solutions, and because neural networks are very good to adapt to different type of data sets, to different type of situations. And in some cases also, if you think about the typical type of approaches that we use to solve inverse problems, they're usually computationally, they get computationally more and more complex and more difficult to solve, the better they work. And with neural networks, in a way, once they're trained, this is not the case anymore. It doesn't work with inverse problems, with the kind of inverse problems I'm interested in, which are inverse imaging problems, and really practically solving inverse problems in practice. It doesn't work to just take a neural network and throw that onto the problem and that's it. So it's actually quite interesting to look into inverse problems also from a deep learning perspective or from a machine learning perspective, because you need to do something more. You need to look back in particular to what people have done more classically to solve these type of problems. And the reasons are just that these inverse problems are usually very, very ill-posed. They're typically, if you think about medical imaging, they map from one function space to another. Think about computed tomography. The measurements live in a very, very different space to the actual image you want to reconstruct. And in practical situations, you can't kill the problem with a lot of training data because you don't have it. And this is the thing that I'm mainly interested in. How can we use deep learning in a way that still gives us solution guarantees in the inverse problems approaches that we want to use to solve a given problem. Okay, so I have here the two parts. Knowledge-driven inversion is just basically a very, very brief introduction to how people classically solve inverse problems. And here I'll also not go into the breadth of what people are doing to solve inverse problems, because you can imagine this is a lot. But I'll focus on one subclass, which are variational regularization approaches. And then I'll talk about data-driven inversion, and in particular this thing that we did 1.5 years ago, which is representing a regularizer through a neural network. Okay, so just to fix notation, in this talk, I have measurements that I denote by y, and I want to reconstruct from these measurements a quantity that I call little u. U could be an image, could be some information I want to extract from an image, but is in my case, in the talk that I'm giving here, always related to some image or image information. And I know how y and u are related to each other, namely by this forward operator t. And then I also assume that this data, which is always the case in practice, is corrupted by some random perturbations, by some random corruptions that I call little epsilon. Okay, so for this talk, I'll assume that I know both the measurements. I know the forward operator, at least approximately, but I assume that this is good enough for me for now. And I also assume that I roughly understand the noise distribution. Okay, so I know what this PE is. Why are inverse problems challenging, interesting for mathematicians? Because they are not straightforward to solve. Even if this capital T is a linear operator, like in this talk, you can't just solve them, not even just because of the random corruptions, but also because this capital T is not invertible usually, because of several things. One is explained here, is this underdeterminedness that we often have in imaging inverse problems, where you don't measure enough to uniquely determine this little u. So you have lots of problems usually with trying to solve these type of problems with noise and stuff like this because of stability issues. You might, in some cases, be able to compute a pseudo-inverse instead of the inverse. This will also come back later, so I'll define the pseudo-inverse as T dagger. And a toy example of such a forward problem that I have in mind, of such a forward operator T that I have in mind, is the radon transform in computed tomography, where what I'm measuring looks like something like this. So this also shows you this idea of having something that lives in two very different function spaces. Sorry, I think I'm going to do it like this because I can't really use the pointer. So you have the measurements y that look like this, which are line integrals through the density of an image, of an object that you image, that is given here, where the parametrization here is with respect to y-intercepts of these lines that you're integrating over and angles. And measuring something like this, what you want to reconstruct is the inside of the human body, let's say. Like in this case, this is an abdominal CT scan of the lung. Okay? So, right, so these are the typical problems. In computed tomography also you see usually it's very easy to explain that you have underdetermined data because you have only a finite discrete number of angles that you are shooting X-rays through the patient, and you usually want to reconstruct a high-resolution image that might have more unknowns than the number of angles that you have shot X-rays through the body. Okay, so this shows you already the underdeterminedness, and the noise usually comes in CT because you don't want to radiate also the patient too much, and just because of physical requirements of the CT machine. Okay, so there are various ways how you can solve these kind of things, and I appreciate there are lots of statisticians here in the room, so you know a lot of different approaches how you can solve such problems. Maybe it's just to say, as a background, I'm a PDE person. This is how I started my career, is to look at nonlinear PDEs. So I'm more in this functional analysis, functional analytic kind of viewpoint onto inverse problems. Okay. So more like this book here, Engel, Hanke, Neubauer, for those of you who know that. Okay, so as a functional analyst, how you think about this is, well, if the problem is ill-posed, what can I do to make it well-posed? And one way is to add regularity to the problem. Or if you think about ill-posedness in terms of being underdetermined, narrow down the solution space by adding an additional penalty to the problem. And this is done in this variational regularization approach as a minimization problem. So you phrase your search for your reconstruction U as a minimizer of a functional that has now your forward model in it in terms of a data discrepancy term. So this is just taking the equation that we had before and putting it into a least squares terms. You want your U to solve the forward model in terms of this least squares fit, at least approximately. And then this is complemented with this regularization term that I call here R of U, that is balanced against the discrepancy term with the parameter alpha. Okay, so this alpha you can think of as a scalar value that basically tells you how much do you need to regularize versus how closely do you want your U to stick to the forward model. Okay? And R of U, you could think of in codes, how do you come up with this? So first of all, R of U, usually you choose to make the problem well posed. So it's called regularizer because it enforces some additional regularity on the solution. You can also think of how you come up with this as having some prior knowledge of the type of U's you want to compute that fit this forward model. So the Bayesian viewpoint, again, is probably very known to all of you, but you can think of this, at least in certain cases, let's say if we stick to finite dimensions, you could think of this as a map estimator of your posterior distribution if you're a Bayesian person. In infinite dimensions, all of this is more complicated, but yeah. Type of regularizers that are very successful and very prominent in inverse imaging problems. So all the time when U is some image or something I'm interested in an image, are regularizers which are sparsity promoting and are edge preserving. Okay? And the total variation is a very good example of such a regularizer. It's extremely widely spread in image processing, image analysis, and inverse imaging problems. And what it is basically saying is that I'm looking for solutions U with a sparse gradient, okay? Which means that I'm saying that most of the information that is important in this image is contained in the edges, is where the gradient of U is large, and where the gradient of U is just, small and not much is happening, you can safely just set it to 0 and approximate the reconstruction U by something constant. So this is roughly the idea, and again, from a functional analytic point of view, this is attractive because in infinite dimensions, the total variation is really the total variation measure of the distributional derivative of U, which gives you that minimizers can really be discontinuous, so they can have edges. So you are edge preserving. And there are generalizations. I'll go into this in a moment. This slide I just have because I love applications. And so I just want to convey to you that there are tons of problems in imaging and image analysis, inverse problems, and so on, where variational approaches like that are being used. Okay, so these are extremely widely spread. Like here in image segmentation, like in image inpainting, where here we are, the image inpainting is that you remove certain layers of paint to look underneath. So this is a disocclusion problem in this case. In medical imaging, we have seen before, or like this is also image inpainting for 3D conversion. So a lot of places where variational modeling comes in, and I'm happy to tell you more about these applications later. One issue, and this is how I also initially got interested in this, with regularization in general, is, and this is the case probably for everyone who is dealing with this also from a Bayesian point of view, is that you have to choose the regularizer, you have to choose the prior. And choosing this is difficult for two reasons. One of them is that the type of regularizers you can choose from, they're usually limited in their capability of modeling something, because you always have to balance the complexity of the term that you put into this variational model against still being able to compute this numerically, right? So you can't, as always in modeling, you also want to be simple. So these are handcrafted models, and therefore necessarily they have limited capabilities of modeling all these different type of structures that you see in images in all kinds of scenarios, right? In all these kind of scenarios, in photographs, in medical images, in satellite images, and all kinds of things. And the other reason, and the other thing is, even if you would be able to narrow down, and you have a wonderful regularizer which can do a lot, how do you, given a set of images, how do you pick which regularizer is optimal for this particular type of application? So this is just, I run through this quickly. This is just to give you a notion that regularization, choosing this regularizer is very important. And again, many of you will have seen this before. And this is an extremely simple example where also the type of regularizer I'm choosing is very simple. I'm choosing as an inverse problem just image denoising, so which means the forward operator T is the identity. And the first regularizer I'm showing you, the result for is the total variation. Okay, so just because we have talked a lot about the total variation, what does it actually do? So this is image denoising. This is my noisy image here. It's very simple still, right? The structures that I'm seeing here are just a combination of piecewise linear intensities. And this is with a cleverly chosen alpha. Okay, this is the solution. This is the solution that I get. So what you can see here, maybe, hopefully, is that you nicely get the edges back. You nicely get the discontinuities. But another thing that I'm not so sure if you, actually this screen is smoothing additionally, is that you also get these blocky-like structures that are called staircasing effect, that come from the fact that the total variation, I mean, thinking about the fact that on the one hand, your solution U should stay close to Y, to your given image, in the least squares sense. So think about, you have a linear intensity, which in the true world looks like this. If I just cut through, this is my intensity profile. And then you have noise on it, so it looks like this. Okay, so the total variation tries to flatten this out because it wants a sparse gradient. But the L2 fit still wants to stick to this oscillatory thing. So hence you get the staircasing effect. Okay, so this is a very well-known artifact of the total variation. But it does well with the discontinuities. Then people have thought about why not combine this piecewise constant idea of the total variation with a piecewise linear idea, because here I have piecewise linear structures here as well, which is done in the following way. So now you phrase the regularizer as an additional minimization problem. So the regularizer itself is given by a minimization problem where you're decomposing, so it's called infimal convolution regularization, where you're decomposing your image into parts where first-order total variation regularization is appropriate, and in another part where second-order total variation regularization is appropriate, which means sparsity in the Hessian. Hence, you get something piecewise linear. And this works fairly well. You see it's still not totally perfect. But now you can go on, right? This is a very simple image still. And in the same flavor, without showing you, results for all kinds of regularizers now, in the same, with the same kind of philosophy, with the same thinking in mind, a lot of people have looked into different types of regularizers, and there are people who really made their careers on thinking about how best to regularize an image. And here, as you can see, when you look at the years, I'm just telling you about the more classical, the ones that I grew up with, type of regularizers. Okay, so nowadays this list is probably much longer, but so there are lots of different types of approaches. Many of you might know about wavelets and sparsity in wavelets or all kinds of LETs. there are also a lot of type of regularizers that PDE people like me have proposed. So coming from a PDE background, again, you could think of having PDEs like parabolic equations, diffusion type equations. They're also smoothing. So a lot of the type of regularizers that people are using also are motivated by differential equations. So there is a lot around, and so you need to choose. And while choosing, you're also aware that is nothing that actually will cover all the type of images that you want to reconstruct or that you want to look at. So in this type of scenario, what I was thinking, and very initially when I thought about this, I did something extremely, extremely simple. So I thought, okay, if I don't know exactly which regularizer I should choose, why not take a linear combination or maybe a finite number of informal convolutions, an n-term informal convolution or something like this of different regularizers and learn the weights, and optimize, just optimize over the weights in this combination. Okay, so this is something we did at the very beginning, and this worked well. It's a tough problem in the end because it's a very non-convex problem you need to solve. Yeah, so this is what we did initially, and I think I have one example to show you this. But with deep learning, this again hit probably a lot of you coming up, it became more and more tempting to think, why actually just stick to a handful of parameters? Now I can go to millions of parameters. And okay, anyway, so I'll show you this, what we did there. So this is somehow the idea. Oh, yes, so thinking about how can you learn a regularizer, okay? By the way, when I go back to this, or maybe I can even stick to here, when you think about inverse problems and variational approaches to solve them, there could be more unknowns and more free parameters than just a regularizer, right? I've just told you at the beginning that I assume I'm happy with the forward model and I'm happy with my noise model. But again, you could think of that these might also provide some degrees of freedom, which you might also want to make more data-driven. But anyway, so I'm sticking to the regularization for now. And here are just just a handful of examples of what people have done, right, in terms of learning regularizers. So one thing is this class of sparse coding or dictionary learning approaches. So probably a lot of you know about that, right? A few. So yes, I know also, so some do know. So here the idea is you stick to this idea that for a regularizer, sparsity is a good thing. So you stick here to an L1 penalty for your regularizer. But you're saying, actually, I don't know in which sense my reconstruction is sparse, okay? And so what you do is that you expand your solution to the inverse problem as a linear combination of different dictionary elements, okay? Just think about those as functions, okay? And then you're learning the weights. You're optimizing over the weights. You're optimizing which of those is important and which not. And you're also optimizing over the functions themselves. So this is sparse coding dictionary learning. Another idea that came up in inverse problems it's a couple of years ago, but that was revived by this paper of Mickey Elard and people and co-workers, was this idea that in image denoising, a lot has happened where people thought about how to get rid of corruptions, okay? Image denoising is a field that is extremely active and is still not solved totally. And so here the idea was, can we not set up a variational problem for an inverse problem, like again we had before, where we take a generic image denoiser and plug it into the variational problem as a regularizer. And they set up the regularizer such that you can do it like this. So this would be the generic denoiser, and now your regularizer is set up as this inner product. Okay. So this is another idea. And this is the idea that we started off, okay, where you have a couple of different types of regularizers. You have like a handful of parameters lambda that you want to optimize over. So your regularizer has a degree of freedom of 5 or something like this, and you want to find the best parameter vector for the regularizer to fulfill a certain optimality criterion. And the optimality criterion that we used and that a lot of people are using and that I will also to a certain extent use is to say I have some exemplar ground truth solutions that I can compare my minimizer with, and that I can optimize the lambda for such that the U lambda is closest to some ground truth U star or something like this. And then there are deep neural networks, and this is something that I want to talk about now. So this is joint work with Sebastian Lunz, who is a PhD student of mine, and Ozan Öktem, who is at KTH. And again, I want to say that this particular work that we did here on this deeply learned regularizers, adversarial regularizers, is really Sebastian's work. So, okay. Before I go there, just briefly, what are people doing in terms of deep learning and inverse problems? And again, this is not at all covering everything. If you want a more comprehensive overview, please read our paper. We published a review last year in Acta Numerica on this topic of data-driven inverse problems. But here I just want to point out, starting with 3 main classes. So how do people solve inverse problems with deep learning? So the first tempting idea that people did in a Nature paper in 2018 was to say, I just phrase my solution to the inverse problem with a neural network. So I call fully learned. I get, let's say, my CT measurements, and I train a neural network to turn these CT measurements into an image. You might imagine that this is challenging because not only do you need the network to do the regularization, but you also need the network to do the inverse Radon transform, right? So this is hence this is not a very desirable approach, and I can tell you more why it's not desirable later. The other idea is post-processing. So post-processing says, okay, one really challenging thing in inverse problems is that I need to do this inverse Radon transform. So I need to go from one function space to the other. Let's just get rid of this by doing a very simple inversion, okay, like the pseudo-inverse, and then use the neural network to clean up the mess that I've created by doing this simple inversion. And then there are iterative schemes where people are trying to interweave the inversion with some data-driven components. So it's a bit, you can think of a bit like a gradient descent scheme where it's also called unrolling, and maybe people have heard about learned vista and things like this. So all these type of approaches I summarize as iterative schemes. Okay, so this I've just said in words. So the disadvantages here, and this what really got us motivated, is there are no theoretical underpinnings to what people are doing currently with where you use a neural network to give you a solution to an inverse problems. There are instabilities, we know about them. There are papers also, especially actually now from the Cambridge group and the group of Anders Hansen, where they actually look into approaches for solving inverse problems with deep neural networks, where they show that actually these are not negligible type of instabilities, they are there. Interpretation, okay, this is anyway an issue with deep learning. And the data consistency is not guaranteed, right? You don't know if you apply that the solution to what the neural network spits out is actually in the range of your forward operator. There are some exceptions. There is a way around this data consistency that Markus Haltmeier looked at with his null space networks, where he can enforce this. But this is more generally the issues that you have. Okay, let me skip this. So what we were interested in is adding another main class of approaches to deep learning and inverse problems, is this learning a regularizer. And so here the idea is really that with these variational approaches, and I've only touched upon what you can do with variational approaches, that we have already a very rich class of mathematical tools at our hands, which are, mathematically founded, where you have mathematical guarantees, you can interpret what is happening. They are agnostic, they're very universal type of principles. But what we also know is that they have their limits in what they can express. So what I want to do is really to think how we can complement what we have here with neural networks rather than replacing. Okay? And I'm interested here in the scenarios where you can't really kill the problem with huge amounts of data. Okay? Which is unfortunately where I'm usually working in. So somehow, and some people might have seen this table before, but somehow what I really would like is to be somewhere in the middle here with what I'm going to present to you now. Okay? Sorry that I have to be short, but now I need to speed up a bit. So what I want, in contrast to the deep neural network solutions in the first three classes, where the neural network spits out a solution to your inverse problem, I don't want that. I want the neural network to act as a prior rather than the one who solves the problem. Okay? Okay, so we are back to our variational problem that we have here. I've said already a lot of things why I like the variational approach, so let's go. So how do we do this? How do we learn a regularizer? And the main idea here, how we learn the regularizer, is that we want to learn the regularizer independent of the variational model. Independent in the sense that while training the regularizer, we don't need to solve the variational model. And the main reason why we wanted this very desperately was the experience we had with this bilevel optimization, where we had this 5 different regularizers and we optimized over the parameters. This is computationally very tough, and for all of you who have dealt with PD constraint optimization might know about this. So this is just very tough to solve, and now we have millions of parameters, not just 5. So we wanted to decouple the two things. And so what makes sense for a regularizer, how to train it. And the heuristics are really like this. So I want, on the one hand, to give the regularizer examples of images that it should like, meaning that it should be small for. And I want to give the regularizer, so these are the type of reconstructions I want to favor. And then I want to give the regularizer, on the other hand, on the other side, images that show the typical corruptions that I want the regularizer to penalize. Okay? Noise, and maybe even, in CT you have these streak artifacts and things like that. And so we do this by basically starting everything with 2 distributions that we set up. One of them is called the distribution PR. Okay? So PR is the distribution that I call here of ground truth images, which means these are lots of examples of the type of images I want the regularizer to be small for, to like. Okay? And then how do I create the distribution of images that I want the regularizer to penalize? And here, this is the only connection where we actually use the information we have about the inverse problem we want to solve, is we want PY to be enriched by the type of artifacts I assume my inverse problem's features. Okay, so this is, first of all, of course, noise. Okay, I can add a lot of noisy versions of the images I have in PR, maybe. Or I can just, if I have an inverse problem, I take measurements, and I do a very simple inversion that I know I don't want, okay? That I know shows a lot of these artifacts, like the pseudo-inverse, like in computed tomography filtered back projection, for instance. And then I take these images as the negative examples for the regularizer. Okay? Okay. And now the Wasserstein distance comes in. Because how do I now evaluate, how do I now, what I just said, how do I phrase this in terms of a loss function? And the idea here is, so don't look at this for now, look here. The idea here, I should maybe go back because otherwise people don't see this. So the idea here is that the argument of this maximization problem here, this f, this should be my regularizer, okay, in the end. And if you look at what I'm maximizing, what I'm optimizing this f for, it's more or less what I said before. If I feed f with samples from this Pn, which is the distribution of noisy versions, I want the regularizer to be large. And when I feed it with versions, ground truth images, with the type of images I want it to like, it should be small. That's roughly what I'm doing. And if I add a one Lipschitz constraint here, first of all, I get regularity that I will later use to prove something about this regularizer and to prove something about the variational model in particular. But I also get this connection to the one Wasserstein distance. Okay, so what this actually is doing here, this is the dual formulation of the one Wasserstein distance between these distributions Pn and Pr. Okay. So how am I doing with time?
7 minutes.
Including questions?
No.
Ah, that's actually good. Okay, I can breathe. So the first thing you might wonder is this something that makes sense? Because later on, imagine, so I mean, one thing you might be thinking of, how do I ever compute this f? And I'll tell you in a moment. But even if you assume you can compute such an f, does it make sense as a regularizer? Because later I want to take this f star and put it back into the variational approach, and I want it to act as a regularizer, right? I want it to act as this thing that brings you closer to the type of images you want to compute. And so a very simple exercise that we did here is to say, well, if I start with a sample from this distribution of noisy, corrupted images, okay? And I take a gradient step in the negative gradient of this f star, okay? Yeah? And I do this for a lot of those u's. I get a new distribution that I call P eta, okay? And now somehow what I would like is, and this is what is said here, that this gradient step brings me closer to somewhere I want to be, okay? And what this here says is that if you do this, then in Wasserstein distance, this new distribution P eta is now closer to the distribution PR. So you are actually approaching, you are going towards this distribution PR, okay? The distribution PR is the one I would desire to compute, okay? So this is kind of nice. So it might be not such a bad idea. But how do we compute this now? And this is where neural networks come in. So I mean, in the end, it's all a bit cyclic, because I told you before we want to use neural networks to do this. Now I came up with this abstract framework. Now the neural networks come back in, okay? So the neural networks come back in the way how I parameterize these f's. And so what I want is, I want to parameterize these f's as convolutional neural networks that take an input as an image, okay, like a regularizer, and that give me a real value that evaluates how good this input is, how good in terms of what I trained it for. Okay, so the neural network takes an n cross m input and gives you a scalar value back. And how do I train this? So here we actually just took the penalty, the gradient penalty approximation, these guys in the Wasserstein gun paper, for those of you who know this, used, which is that, remember, we had this one Lipschitz constraint. We had this one Lipschitz constraint for f, which we now add as this gradient penalty. We phrase it basically by saying that the norm of the gradient of psi theta should be 1. Okay, so this is basically what roughly we are doing. Okay, this is another topic: how closely, why this is still a Wasserstein distance. It's probably not, but yeah. Okay. So in summary, what we are doing is we train a regularizer in this manner with this loss function. We optimize here over the parameters theta, right? And then we take the psi theta, plug it back into the variational model, and then be happy and solve for new data y. One thing that I want to emphasize, because this is actually quite nice for inverse problems, is, or I can stay here, is that these samples in the distribution PR and the samples in the distribution Pn, they don't need to be paired. Okay, which means that for the type of measurements I'm taking, I don't need to know the ground truth. I just need to be able to simulate or create images that I put into PR, which I think resemble the type of reconstructions I want to compute. Okay, so in that sense, how we are training the regularizers is actually unsupervised. Okay, does this make sense to everyone? Here I'm integrating, right? So I'm not comparing things point-wise. Okay, I'm evaluating the overall distribution. Okay. So how does this look? And this is just an anecdotal result that I'm showing you here. So remember, this is computed tomography. So my measurements are this projection data that I've shown you at the very beginning. Here, the first column is a typical example of a sample from PR, the type of images I'm training the regularizer on that it should favor. Here is a typical example of the type of samples that are in Pn. I told you for inverse problems what we do if the pseudo-inverse exists. We create those samples with the pseudo-inverse with the filtered back projection in computed tomography. So these feature the noise and the corruptions. I know my forward operator somehow features. This is total variation, so it's actually not that bad in a way. This is post-processing, so this means we take the filtered back projection and then we train a neural network to get closer to here, okay? And this is what comes out of this learned regularizer. By the way, we called it adversarial regularizer because it is trained in this adversarial fashion, right? Yep, thank you. I'm actually done. In the results we have so far, actually the adversarial regularizer is not doing that badly. It's certainly much better than these type of handcrafted regularizers like the total variation. But it is not yet better than the post-processing. Okay, so this is actually interesting. But let me just emphasize that post-processing is supervised and also post-processing, they can't prove what I'm now going to tell you. So maybe I'll quickly tell you what we can prove, and if you want to know more, ask me later. Okay. So we can prove at least existence and a very, very weak notion of stability. Okay. And we are at the moment working on how to train the regularizer, how to constrain the regularizer more to be able to prove more. Okay. But that's what we are doing at the moment. That's what we can do at the moment. So we can prove existence of this, where for those of you who know about existence proofs, and well probably all of you, we get the course. So this is all in infinite dimensions, by the way. We have images and data in two infinite dimensional Banach spaces X and Y. And T is a linear operator. So that maps from X to Y. And so what we can prove is that solutions exist if either my forward operator is well behaved, or I can ensure, and this is something that we can do in the training, that this regularizer is bounded from below. Okay, so this is an issue that we don't usually have. So we can live also without the boundedness from below if this operator T is injective. If not, then we need the boundedness from below that we need to enforce in the training. Okay, so we can prove existence. And then the weak stability is we can't at the moment, with the assumptions that we have on the regularizer, prove more than a weak stability. Weak stability just means that if I have a sequence of data that converges in norm topology to a data y, then the corresponding minimizers weakly converge to an x, which is a minimizer of the problem with this limiting y. Okay, so you get some type of stability, but yeah. Okay, takeaway messages. So as you can tell, I'm a big fan of variational models and, well, PDs as well. But I think what we have been doing, and what is probably what a lot of us are doing at the moment, is to try to fit and try to see how we can use data-driven components like deep neural networks in a context that we understand, in a context where we can still analyze and prove things about the solutions we get and things like that. So I'm in particular interested in deep variational models, as I've shown you now. The adversarial regularizer was really meant, or really worked with this idea of parametrizing with respect to distributions of desirable and undesirable type of images. And the advantages of doing something like this in this variational context is that we can prove things, okay? The data term allows maybe also to say data consistency is just given because we solved the variational model in the end. We also still have a handle on the noise model and things like this. We can all model everything that we usually have in the likelihood and in the data discrepancy term. We can all still model, right? This is something I'm sticking to. We can prove some things about it. It's an unsupervised approach, okay, through training on distributions. And the disadvantages, of course, and this goes back to my very first slide, where I said deep neural networks are also interesting for inverse problems because they're computationally cheap. How we are doing it at the moment, at least, is not computationally cheap anymore, because we are, in the end, still solving a variational model, which is expensive, especially now that we have a non-convex regularizer. Okay, so the philosophy is learning structured but adaptive imaging models, and still in a way that we can prove things about them. And I would like to thank the Cambridge Image Analysis Group, because without them this would really not be possible. And I thank you very much for your attention. Thank you.